Okay, here we need to differentiate this expression, the quantity x squared minus 3 raised to the cosine of x. Now that right there should draw your attention immediately. We have a variable in our exponent. This means we cannot apply the normal power rule, where we simply bring down the exponent in the front and drop it by 1, because that only applies when the exponent is a constant. And we don't have that here. Now you might think, well, I've seen some variables in the exponent before, for example, e to the x, or e to the x squared, or e to the cosine of x. That would be fairly easy to do. But notice we don't have e sitting here either. This also has a variable associated with it. The base of our exponentiation has a variable associated with it. So what do we do here? Wouldn't it be great if somehow I could move or otherwise eliminate this variable out of the exponent? We've seen cases where we can do that before. Recall the properties of logarithms. These three might spring to mind. Things like the log of a product can be expressed as the sum of logs. The log of a quotient can be expressed as the difference of logs. And here, the important one for us, the log of a power can be rewritten as the product of that power and the log of the thing being raised to that former power. You see, this rule here allows us to move exponents out in front of logs. Now, the downside of this is, in our expression, we don't have a log to move this in front of. This doesn't apply immediately. But what if we could manufacture a natural log or other log in just the right place here? We can do that, as it turns out, if we remember one other property, and that is that logarithms and exponentials are inverses of one another. In particular, e to the ln of anything, say y, is going to be that same thing, y, right back. E and natural log are inverses of one another. They cancel each other out. So we can take advantage of that here. We can rewrite this as e to the natural log of this. So now we have e to the natural log of x squared minus 3, and that is raised to the cosine of x. Now we do have a natural log of a power, and I can take this exponent here and pull it out in front to get e to the product of cosine of x and ln of x squared minus 3. And this is something we know how to deal with. This is just e to some function of x, and we can use the chain rule here to say the derivative of e to this something is e to the same something times the derivative of that something. Okay? So let's erase this so we have some more room. Okay, so when we start to take the derivative here of y, again, this is e to the something, so the derivative should be e to that same something times the derivative of that something. Of course, this something right here is a product, so to take its derivative, we'll have to apply the product rule. We've got a first guy times a second guy. The product rule tells us the derivative of that is the first guy times the derivative of the second guy. But the second guy is a natural log of something. And we know the derivatives of natural logs of things are 1 over that thing in question, and by the chain rule, times the derivative of that thing. Of course, the derivative of x squared minus 3 here is simply 2x. Okay? Plus, remember where we are, we're in the middle of a product rule. We have the first guy times the derivative of the second guy, plus the second guy times the derivative of the first guy. Of course, the derivative of cosine of x is simply negative sine of x. Okay, so we have the derivative of y. It remains to clean it up, to simplify it. Now, with that in mind, Note that whenever we pull this trick, that whenever we see some sort of variable expression raised to some sort of variable power, and we rewrite that as a power of e, where a natural log is involved, so that we can take that variable exponent and yank it out front of the natural log, so that we can proceed with our normal differentiation rules, we're using the process of logarithmic differentiation. Okay? And when we do that, we always get e to the something that we're differentiating up here. Okay? And this e to the something is equivalent to our original expression here. So when we differentiate e to the something, when we're using this technique, we always get e to the same something in our derivative and then times a bunch of other stuff. Okay? This piece here in logarithmic differentiation will always be identical to this piece here, which is just another version of this. So to simplify this, let's realize that all of this is just this. And then we have all of this stuff here on the end. We can always do that move, that simplification move, when we're differentiating logarithmically. Okay? Now, as for this other piece here, what we can do to clean it up, well, there's not a whole lot. We could maybe put the 2x in the numerator. If you want, you could put the cosine in the numerator, or we could just put it over here on the side. That's fine. Plus, well, we have this product here, and depending on how you write it, there could be some confusion over whether or not we're taking the natural log of just x squared minus 3 or the natural log of the product. So to avoid that confusion, we really just want the natural log of x squared minus 3, and then all of that times negative sine of x. We either need to really put some brackets in here, or we could move the sign to the front. Of course, since it's negative, that changes this plus to a negative as well. Okay, so now we have minus the sine of x times natural log of x squared minus 3 there to complete that expression. Okay, and that's about as far down as we would want to simplify that. All right, so this right here is the derivative that we sought. We are done. Okay, let's take a look at another example. Here we have the natural log of x, all of that raised to the x power, and we have to find the derivative of this guy. Okay. Now again, having this variable in the exponent and variables down here in the base of the exponentiation causes us a bit of a problem, in so much as we can't use the power rule. We can't use a formula for e to the x directly. This is a candidate for logarithmic differentiation. Now, be careful here. We know we want to move this variable out of the exponent. We know we have this nice property of logs that we can exploit to this end, namely this guy right here. But notice we cannot do that right now to this expression. We cannot pull this x in front of this natural log, because this is not the log of a power. This is a power of an entire log. In other words, this little exponent x here doesn't go with this x. It goes with the whole thing. So we again appeal to this trick of writing this thing as e to the natural log of this thing. So I'm looking at e to the natural log of the natural log, all of that, to the x. Now this is the natural log of a power, and so the exponent on that power can be pulled out in front, and so we get e to the x times the natural log of the natural log of x. And now we're in good shape, because we can finish off this problem. We can take the derivative with our normal differentiation rules. This is just e to something, after all. And so the derivative of f should also be e to that same something, and then by the chain rule times the derivative of that something. Okay, so we need a derivative here. Notice that the something here is a product again. And so we'll have to use the product rule. So we have a first guy, we have a second guy. Product rule tells us the derivative of this whole thing is the first guy times the derivative of the second guy. Now the second guy here is natural log of something. And the derivative of natural log of something is 1 over that something times the derivative of that inner something. Of course, the derivative of natural log of x is simply 1 over x. Don't forget where we are. We're in the middle of a product rule. We have the first guy now times the derivative of the second guy plus the second guy, ln of x, times the derivative of the first guy. Of course, the derivative of just x is 1, so I don't need to write times 1 here. Now, the differentiation part is done. We just have to clean up our answer. And here again, we can always expect this piece in the front, this e to the something, that resulted from differentiating this e to the something, to be the same e to the something. And that e to the something, again, is just another form of what we started with. So I can replace this guy with this guy. So let's write that down. And then times, and then we just do whatever we can to make this a little bit clearer. Notice here the x's cancel. And we're left with 1 over ln of x plus natural log of ln of x. And we are done. That is our final simplified derivative, f prime of x, if that's f. That's it. Okay, here again we're differentiating some expression, and we're going to be able to see exactly when it's necessary to insert this e to the natural log of something to help with the differentiation, and when it's not. So looking at our expression here, we see that it's a sum or a difference of 3 different things here. The first thing is natural log of x to the 2x power. Yes, we have a variable exponent on a variable base here. We'd like not to see that if possible. Fortunately, there is already a natural log sitting right here. This is a natural log of a power, so I am free to move this 2x to the front to rewrite this expression for y. So this becomes 2x times the natural log of x. Just that piece. And this we know we can proceed with our normal differentiation rules and crank out the derivative for it. This term, however, very similar to the last example we did, is a variable exponent on a variable base here. There's no natural log that I can use to bring this 2x out in front. Remember, this natural log won't work. This is a power of a log, not a log of a power. Okay, so in this case I'm going to have to insert the log I need. So I'm going to have to rewrite this as e to the natural log of this mess. Okay, so that becomes e to the natural log of x to the 2x. Okay, and then I'll be able to pull that 2x out in front. All right, and we'll do that in the next step here. Looking at the third term, what do we have here? Well, we have a variable in our exponent, but our base is a constant. And what's more, this is natural log of e to a power. Natural log and e to a power, those are inverses of one another. Natural log of and the e will simply cancel out here. Another way to see this is we could pull the x squared out in front of the natural log, and then simply natural log of e is just 1. Either way, you get just x squared when you're done. Okay? Now, we said we were going to go back and do something to this term. Let's go ahead and do that. We still have a 2x ln x here. And the advantage of writing it in this way is that we could take this 2x and pull it out in front of that log. So now we have e to the 2x times the natural log of x. And then don't forget your minus x squared here from that guy. Now, I can take the derivative of what I have here with my typical differentiation rules. Okay? Looking at the first term, let's give ourselves some room here. We'll say y prime is over here. This guy right here is a product. So it looks like we'll have to use the product rule. So we have first guy, or 2x, times the derivative of the second guy, which is 1 over x, plus second guy, which is ln of x, times the derivative of the first guy, which is just 2. And I'll put the 2 in the front here. Looks a little bit prettier that way. So all of that is the derivative of this piece. Now we move our attention to this. This is e to some power, e to the something. So the derivative of e to the something is e to the something times, by the chain rule, the derivative of that something. Of course, notice the something here is a product. So we'll have to use the product rule to find its derivative. So this is first guy, this is the second guy. Product rule says we need first guy times the derivative of the second guy. Of course, the second guy is the natural log of something. So its derivative will be 1 over that same something times the derivative of that something. And of course, the something here is ln of x, so its derivative is 1 over x. Okay, remember where we are. We're in the middle of a product rule. We now have the first guy times the derivative of the second guy. First guy times the derivative of the second guy. We need to add the second guy times the derivative of the first guy. Of course, the derivative of the first guy is just 2. So maybe we'll squeeze it in here instead, as that looks a little bit prettier. Okay, so that concludes the derivative of this something. But don't forget, we have one more term here to differentiate. So the derivative of x squared, of course, is 2x. Okay, it remains to clean things up. We're done with the differentiation. All we got to do is simplify now. Notice these x's cancel. So we have a 2. We have a plus 2 ln x from this guy. When we look at all this mess, remember, this here is identical to what we had in the original function, that one term anyways. And that one term was just a different form of that term. So let me replace this with this. So we have plus ln of x to the 2x times, and then we have to simplify what we see here. Again, some x's cancel there. So now we have 2 over ln of x, and plus, and there's not much we can do with that, so 2 times ln of x, and then minus 2x on the end. And that right there is our derivative. And we're done. Okay, in this problem we need to find the derivative of this expression. And this is kind of a nasty looking expression here. Let's think about this. If we were to attack this directly, we might say, well, let's see, overall here it looks like I'm looking at a composition of the natural log function and this rather ugly expression here. So I could use the chain rule. But then I'll have to take the derivative of the inside, and that looks like that's going to involve the quotient rule. And of course, within the quotient rule, I'll have to take eventually the derivatives of the numerator and the denominator, and that looks like that's going to take in turn an application of the product rule for the numerator, and the product rule down here in the denominator, and then inside of the product rules, inside both of those, we'll have some chain rules going on. That's a lot to have to worry about. Always be aware of how you might take your original function, which you wish to differentiate, and simplify it to make the differentiation process easier. This is one of those cases. We can appeal to the properties of logs to write this in a much more differentiation-friendly way. Now, what properties of logs am I talking about? Well, these are the big three. So when I'm looking at this, I'm seeing a natural log of a quotient. notice this applies. I could rewrite a log of a quotient as a difference of logs. So let's do that. So now we have the natural log of the numerator minus the natural log of the denominator. But in looking at both of these, can't we pull a similar stunt? This is the log of a product. And the log of a product can be expressed as a sum of two logs. So let's do it again. So just breaking up this guy, we have natural log of x cubed plus natural log of e to the sine x. Now we can turn our attention to this, but here again, notice we have a natural log of a product. So we are subtracting here the natural log of cosecant of x plus the natural log of x squared. Now be careful here. Notice this says you're subtracting the natural log of all this. All of this is all of this. We need parentheses here. Otherwise we're going to lose a distributed negative right there. That's a very easy mistake to make. Already this is looking much nicer, especially since we are able to differentiate things term by term. But there's still more we can do. Look, this first log is a log of a power. And what can we do with powers? We can bring them outside of the log. Notice we also have a log of a power here. So we should be able to bring this sine of x out in front. And even here we have a log of a power, so we can bring that 2 in front of this log anyways. So making all of those changes, we get 3 ln x plus sine of x times the natural log of e. Of course, natural log of e is just 1, so I don't have to write that at all. Minus natural log of the cosecant of x, and plus the natural log of 2 times the natural log of x. And if I go ahead and distribute that negative, that changes this to a negative. Okay? So now this is looking much more differentiation friendly. And in fact, at this point, let's go ahead and crank out y prime. Of course, we proceed term by term. Again, we're looking at a sum or difference of several different things. The derivative of 3 ln x, of course, is 3 over x. The derivative of sine of x is, of course, cosine of x. And the derivative of ln of cosecant x, there's actually a couple of different ways to go here. One way, perhaps the fastest if you see it, is to realize that cosecant x is simply the sine of x raised to the negative 1 power. And I could pull that negative out here and turn that into a plus, and then I'm just looking at natural log of sine. Or we can proceed directly and say, well, this is natural log of something, so its derivative should be, let's see, minus from that, 1 over the something times the derivative of the something. Of course, the derivative of cosecant x is negative cosecant x times cotangent of x. And then we can see the cosecants here are going to cancel, the negatives are going to kill each other off, and all I'm left with will be cotangent of x. So making that change, let's turn our attention to this last guy here, which is minus the natural log of 2 times the natural log of x. So here again, we pick up the minus from this guy. We have natural log of something. The derivative of that should be 1 over the something times the derivative of the something. But the derivative of 2 ln x, of course, is simply 2 over x. Okay, so that completes the differentiation. All we have left to do is simply simplify it, and there's not a whole lot we can do here. We still have 3 over x. We still have a cosine of x here. We still have a cotangent of x. Nothing really we can do with those. Here, the 2's cancel, and so I have 1 over ln x times x, and just to avoid confusion there with what I'm taking the natural log of, I'll put the x first. So x ln x. Okay? And that is our derivative. We're done.